Okay, so what we're going to do first, we are going to continue to talk about Laplace inverse, okay? So this means that the Laplace of the function will be given to you. You would like to find the original function. It's like integration, the opposite operation. So to give you a couple of them, there are a couple of more that it's different. So I just continue with that last example. So the example was this one, that find the given inverse Laplace transform. Because when you want to solve the differential equation, this is going to be your main job. You're going to get a couple of them at the same time when you want to do it, okay? So we did, these two was straightforward, so let's get a couple of more. These are very popular ones, the one that we are going to see. So we continue, that was number 3, number 4. We want to find, this is very, very popular. This example, or this is less popular, okay? It's going to be Laplace inverse of this function. S over s squared plus s squared plus 2s minus 3. So this is the one. So we talked about it the other day, but we shouldn't have to break it. That's done as a partial fractions, if you like. Okay, take care of it. So there are going to be two groups. The groups that the numbers are not going to be factorable. You have to go kind of completing the square method. You cannot do it now because we don't have that function that will be related. We're going to do it later. But so the one that we're going to have so far are going to be factorable. The last one to get your two next test. The next one are going to be the one which is not factorable. If you use this one, so you know we factor it to see how we are going to write it down as a partial fraction. So this will be s, two numbers. I give you s plus 3 times s minus 1. Okay. As in the case of integration, we break it. So this is going to be s plus 3, something like on the top a, b. I'll go with the a1. Okay, and plus the second one's going to be s minus 1. Let's go with the a2. You have to find the common denominator, get the top to equal to each other, find the a1 and a2. So we say to the right, and we continue. So that would be s plus 3 times s minus 1. The first one would be a1 times s minus 1 plus a2 times s plus 3. So let the top to be equal to each other and find those numbers. So the top over here is s, and the other side a1 times s minus 1 plus a2 times s plus 3. Okay, this must be equal to the s. Okay, you know that. You can multiply it and just consider it the equality of two polynomials, or you just use two numbers, two nice numbers to find it. You know, the nice numbers are going to be zeros after the denominator. So we put s equal to 1. If you put s equal to 1, this would be 0. Okay, and the second part would be a2 times 1 plus 1 equal to the 1. So that gives it 2a2 is equal to 1. So a2 would be equal to the 1. Okay, this is how we find the a2. Yes.
Wouldn't it be 1 plus 3 inside the parentheses? Yeah, 1 plus 3.
Oh, yes, yes, thank you. That's 1 plus 3. So that gives you what? That gives you 4. So that gives you a quarter. Okay, so it's going to be a quarter. We repeat it again. S equal to the negative 3. S equal to negative 3 is going to be a1 times negative 3 minus 1. The second one would be 0. And this would be negative 3. So we get negative 4a1 equal to the negative 3. And the a1 would be 3/4. There you are. We go back, we rewrite it, we break it, we use the linearity, and we get the result. Okay, so we are going to end up with this one. We want to find the Laplace inverse. Okay, Laplace inverse of a1 is 3/4, so it's going to be 3/4 over s plus 3 plus a2 is 1/4, a quarter over S minus 1. You know that. You pull out the numbers, both of them are going to be exponential function. Remember, Laplace of e to the at is 1 over S minus a. So this is going to be 3/4, okay, 3/4 of the e to the negative 3t, the first one. And this is going to be 1/4 e to the t. Just using this formula, that the Laplace of e to the at, remember, is 1 over S minus a. So anytime it's going to be of this form, we write it down that way. Numbers, you know, it's a linear, you put out the numbers, and then you get the result, you write it. Any question? We're going to see this one a couple of times when we get to the solving the equations. So there is going to be one more format that it can be done by a short form. So that's number 4. Any questions? So be ready for it to break it. The only question is going to be if this is not going to be factorable like integration. Remember, in integration, you make it into the perfect square and then you tangent inverse in integration. It's going to be something similar over here. Okay. So let's check the next one. Again, this next one is going to be very, very common. And you can use a shortcut to find it. So this would be our the 5th one. Okay, you want to find the Laplace inverse of 1 over S squared times S squared plus 4. Dealing with the sine and the cosine, this would be very frequently appear in the solutions of the differential equation. Okay, again, you have to break this one. Look at the breaking one. This is going to be 1 over S squared times S squared plus 4. You see, official breaking for integration is like one. You start with the S, remember, S squared, then you go S squared plus 4 because it's a repeating factor. And you're dealing with the Laplace transform. In the case of the Laplace transform, 1 over S squared and 1 over S squared plus 4, it's, can be done. You have something for it. So you don't have to break it in full details like integration. So you break it into this format. You break it to the format that you get S squared, okay? And you get S squared plus 4. This is going to be your target. Now this can be done by a shortcut that I talked about it. You see? You need a constant here. So whatever you put on the top of these two, you should be able to eliminate S squared. There is no S squared over here. So put two opposite numbers. It doesn't matter whatever it is. So the easiest one is 1 and negative 1. So if you put something like 1 here and the negative 1 here, quickly you may check it to see if you get this right. So if you've done it, you know that the denominator would be S squared over S squared plus 4. The top would be what? 1 times S squared plus 4. Okay, minus S squared. So this would cancel out. This would cancel out. The result would be what? The result would be 4 over S squared over S squared plus 4. But you need 1. So what we're going to do, you divide these two by 4. Normalize it if you like. So you go back, you say, oh, so this must be a quarter, and this must be a negative quarter. Quickly can take care of it. So don't try anything algebraic. It takes so much time to be able to do it. Okay. So anytime you want to, you have to remove the S squared. So put two opposite numbers on the top. It doesn't matter. Two opposite numbers in any directions. I put the 1 and negative 1. So find the common denominator. The top would be S squared plus 4 minus S squared. S squared and S squared would cancel out. You get the 4. But you need it to be 1. So what you have to do, you have to go and modify it. You divide by 4. Okay, any question? Now we can find it. So now the Laplace inverse. Okay, the Laplace inverse will be changed to what? Will be changed to a quarter over S squared. I rewrite it minus a quarter over S squared plus 4. Pull out this number and then take the inverse. It's going to be a quarter Laplace inverse of 1 over s squared. Okay, and this is going to be negative quarter Laplace inverse of 1 over s squared plus 4. That's it. You know that 1 over the power of the s, that gives you the power of the t. Remember, Laplace of t to the n is n plus 1 over n factorial over n plus 1. So this simply would be what? So I'm going to use these formulas. Look at this formula. Laplace of t to the n is n factorial over s to the n plus 1. That's the formula that we have. Okay, in this case, n is equal to 1. So 1 over s squared simply would be what? So the Laplace inverse of 1 over s squared is simply t. Usually do this right away. Okay, just go with the first one. Any question? What is the second one? The second one, you get s squared plus 4, but only a number on the top. Remember, if it's only a number on the top, it's a sign. If it's going to be s on the top, is a cosine. So it's s squared plus 4. S squared plus a squared we have. A squared is 4, so you need a 2 on the top. So the second one would be, this is the Laplace inverse of 1 over s squared plus 4. You need a 2 on the top. So you divide outside by 2, and you multiply the inside by 2. So that gives you 2 s squared plus 4. Now the inside one would be sine of the 2t. Okay, in practice, we do it the right way. You know, when we get used to it in a couple of minutes, if you like. Okay, so the final answer would be, so there you are, the Laplace inverse of 1 over s squared over s squared plus 4. But it's going to be a quarter of the t minus a quarter times a half of sine of 2t. Okay, so the final answer is a quarter of the t minus 1/8 sine of the 2t. This will be the final. And you will see it in a minute. The first differential equation I'm going to solve for you, you will see it right away. Okay, so this one of those tricks is very, very popular, and we're going to do it. Any question? Just give you one more, because this one is not going to be used quite a lot, but you have some problems in your book that give you this type of format. So we can do it quickly. This is going to be Laplace inverse, the Laplace inverse of 1 of s minus 1, like integration in calculus, s plus 2 times s minus 4. See, you have a kind of trilinear factor down the denominator. So you write it down as a partial sum. Since you have 3 factors, you're going to have 3 fractions. Okay, and you have algebra to find it. So this is it. This is 1 over s minus 1 times s plus 2 times s minus 4. So the first one will be s minus 1. You get the a1 here. The second one will be s plus 2. You get the a2 here. And the last one is s minus 4. You get the a3. Okay, you stay to the right, find the common denominator, prepare the top, let them equal to each other, and you have 3 nice numbers quickly, you can find it. So I'm going to continue to the right. So the common denominator, s minus 1, s plus 1, s minus 4. So the top, first one, we drop this one, it's going to be a1 times s plus 2 times s minus 4. Second one, a2 times s minus 1 times s minus 4. Last one would be a3 times s minus 1 times s plus 2. Okay. So you let the top to be equal to 1, and you check those 3 numbers right away. Some short form, I did that. Okay. Okay. So I'm going to rewrite it and find it. Okay. A1 That's a S plus 2 times S minus 4. Then I have the A2, S minus 1 times S minus 4. Then I have A3, and that's S minus 1 times S plus 2. Everything equal to 1. Zeros after the number 1, negative 2, 4. So substitute it. S equal to, I go with the 1. If you put 1, you get only the first one. A1, 1 plus 2, and 1 minus 1. Everything else would be 0. Because you have S minus 1 and S minus 1. So that would be equal to 1. Okay, so that would be, this is going to be 3, and this is a negative 3. So that gives negative 9A equal to 1. So A1, so A1 would be negative 1. That is going to be your. Okay, any question? Check the other numbers.
Can you move it just over to the side? Thank you.
Okay, so S was 1, so we check S negative 2. S equal to negative 2. Negative 2, this would be 0. We're going to get the middle one. A2 times negative 2 minus 1 times negative 2 minus 4. The middle one would be also 0. On the other top is 1. And so that would give us a negative 3 and the negative 6. Okay, so you get 18 A2 equal to 1. So A2 would be 1 over 18. So that would be A2. And repeat it again, S equal to 4 to get the other one. So S equal to 4. This would be 0 because of the S minus 4. The second one would be 0. So we get only the third one. So this is going to be 4 minus 1 times 4 plus 2 equal to 1. So that gives you 3 and the 6. Okay, again, that make it to the 18. So 18, A3 is equal to 1. So A3 would be 1 over 8. If you go back substitute, they are all exponential functions. Okay, so this will give you, remind you the procedure that you're going to have. Okay, are you done? So break them into this new format. Okay, original one. So you are going to be finding Laplace inverse. A1 was a negative 1,9, negative 1,9 is minus 1. And the other one was 1 over 18. Okay, S plus 2. And the last one again is 1 over 18. 1 over 18. And that was S minus 4. To break it, you pull out the numbers, they are all exponential. So this is going to be negative 1,9 e to the t. The other one is 1 over 18 e to the negative 2t. And the last one is 1 over 18 e to the 40. And it's a linear format, it's all exponential function, and then does that. Okay, any question? We're going to have much more in future, but it will be so easy. It's going to make give you a couple of theorems, okay, then you can find the other one, you know. But you need this basic one. Now, this is the time to start solving differential equation. Okay, we are going to do 2 groups of differential equation. The first one is the one that we can do it so far. The second group are going to be the one that involve piecewise defined function from sets. These are going to be a little bit more, not complicated, more involved. So for the time being, let's check the ordinary one, or check the solution. How we're going to find solution of the differential equation. This differential equation must be linear with the constant coefficient only. The one that we consider, okay? There are some nonlinear that we can do. But to start with, we are going to consider you are going to be given a linear equation with a constant coefficient with the given initial values. All the initial values will be given to you at 0 only. Okay, so it's a kind of, we call it boundary value problem or initial value problem. So what we're going to do basically, if a differential equation is given to you, everything is linear. So we're going to take the linear, you're going to take the Laplace transform of both sides. If you take the Laplace transform of both sides, all the numbers would be the leftover, the coefficient, because they are constant. So you end up with the Laplace of y, Laplace of y prime, Laplace of y double prime. It depends. How many do you have? So what we are going to do, we are going to give a nice theorem. There is going to be a theorem that enables you to write the Laplace of any order, the derivative of any order, derivative of Laplace of the derivative of any order in terms of the Laplace of the given function. For example, if you have Laplace of y double prime, you can write it down in terms of Laplace of the y. Laplace the y tiers, okay, the third derivative, Laplace the y. So what you do is you use this theorem, you change everything to the Laplace of the y, Laplace of the y. Then is algebra. You are going to have an equation in which the unknown is Laplace of y. So you solve that equation. You solve that equation, you get Laplace of y on one side of the equation, the function of s on the other side. You take the Laplace inverse. That. So this is the way we do it. So the key one is this theorem. How we're going to express Laplace of the derivative of the function in terms of the function. It's a very nice theorem. I'm going to prove it for you. It's very important theorem, and then we're done. We can do, the solving equation. So this is 7.2. Okay, it's a very dense section. Okay, but we do it step by step in this section on the function. So solving. Okay, solving a linear differential equation. Linear differential. Linear differential equations. Okay, of course, with the constant coefficient. With the constant coefficients. Of course, then using Laplace transform. Using Laplace transform. See, as I talk about it, in order to do it, the key is this theorem. You know this theorem, then you're done. Theorem, we're going to express the Laplace of the derivative of the function in terms of the Laplace of the function. So take this function. If the function, let's say f is going to be differentiable. It's going to be differentiable as usual on the domain that you are interested in, 0 and infinity. Okay, look at this one. Laplace of the derivative of this function. Laplace of f prime of t is equal to the s and the Laplace of f of t minus f of 0. That's it. If you prove this formula, then you can replace f prime. You can replace f by f prime. This would be f double prime. You can do f double prime for the third, for the fourth, and then for the. And the key is to prove this one. Okay, let's prove it. How are we going to prove it? Definition only. Okay, how do we prove? Nice to know how we prove these theorems. Okay. When we go on for the coming, not this quiz, okay, for the other one, usually ask you to prove something short for us for the Laplace transform. Okay, so let's do it. Definition on. What is definition of Laplace of f prime of t? is equal to what? Integral 0 to infinity e to the negative st function. What is the function? Function is f prime of t d of t. This is going to be the one that you want to find. Okay, let's work on this integral. You would like to write it down in terms of what? You would like to have something like e to the negative st ft dt. So the way we're going to do it, just we are going to apply the integration by parts to integrate this function. Okay, so let's do the integration by parts for this one. For the time being, forget about 0 to infinity. E to the negative st f prime of t dt. So what I'm going to do, I'm going to use the integration by parts to get this one. Any suggestion for you and the b? Any guess? Yes.
I'm just making
V is
just T.
V is F5 of C.
Which one?
V is F5 of C.
No, it's not.
I was wrong.
Not V. You mean
dv.
Right.
D.
Well, F5 of T dt would be dv.
Yes.
That's why I'm saying F5 of T. Oh, I see.
Because you have to integrate.
Yeah.
You see, since you want to integrate it, you get f prime. When you integrate f prime would be f. So that's why. So take u to be e to the negative st. You see that's one. Now dv would be now f prime of t dt. Now the other part are going to be what? du would be, remember, with differential respect to the t. Differential respect to the t, exponential function never change. You have to find the derivative of the top. Respect to the t would be negative s. So that gives you negative s e to the negative st dt. That's your du. Then you have to find your v. If you want to find the v, it's going to be just f of t. F of t. Now go back and write the integral. So what I'm going to do, I'm going to have the integral from 0. Eventually, you have to find 0 to infinity. It's improper integral. So we have to find something like 0 to b first. Then we take the limit. Okay. So e to the negative st f prime of t dt is going to be equal to integration by parts formula u times v. This is going to be uv. So it's going to be e to the negative st f of t, and it's going to be defined from 0 to b. Okay, uv minus integral of what? v du. v du. So v du would be what? This is here. So that gives you f of t times negative s e to the negative st dt. Okay, dt. But this integral is going to be defined from 0 to b. We find it from 0 to b and take the limit, b goes to 0. Okay, let's work on this one. Substitute equal to substitute for t. So this is going to be e minus s sb if you t equal to b, f of b minus this one, replace t by 0. So minus e to the 0, f of 0. To substitute from 0 to b, I put t equal to the b, this is t equal to the b, and this is t equal to the 0. Okay, and the rest over here, you can't do match, but this integral is respect to the t. So s will be considered as a constant. So we can pull out the s, negative s. Bring the negative s out, negative will be positive, so that gives you a positive s integral from 0 to b e to the negative st ft dt. So that's one. Any question? Okay, so what else are you going to do? You have now to take the limit when b goes to infinity to get this number. I'm going to rewrite this one again, okay? I'm going to put the Bring this one down, it's going to be f of b over e to the sb. E to the 0 would be 1, so that will be minus f of 0. And this is going to be s0 to b e to the negative st ft dt. Okay, any question? Now take the limit when t goes to infinity. Treat as is. If t goes to infinity, what will happen? You see, if t goes to infinity, if t goes to infinity, this part over here is going to be 0 to b would be 0 to infinity. So that gives you 0 to infinity. 0 to infinity, e to the negative st, okay, f prime of t dt. That's what will happen to the right, to the left. And what happened to the right? When you go to the right over here, you see, condition that we did have before, b is positive, and you can force s as it's going to be a positive over here, because the domain of the function is 0 and infinity. So what it is the number that goes to 0. And f of b on the top is just an f of b. F is a continuous function. It's a continuous function. We can consider this one to be a bounded. So the absolute value of b is going to be less than something. So it's like you have a bounded on the top, and the number that goes to infinity, so this goes to 0. Okay, so that gives you 0. So the leftover would be what? The leftover would be negative f of 0 and plus s. This integral is 0 to b. When you let t goes to infinity, that gives you integral 0 to infinity. E to the negative st ft dt. That's it. In the language of Laplace transform, so what you have, this is going to be Laplace of f prime. So this is going to be Laplace of f prime of t is equal to what? Negative f of 0 plus s, and this is Laplace of f of t. Laplace of f of t. That's it. If you rewrite it, this is what you are looking for. So basically, we proved the formula. We proved that the Laplace of f prime of t is simply s times Laplace of f of t minus f of t. It's a nice theorem. I'm going to give a couple of more things that you have to prove it for us. And so it's good to know this method. Okay. So that would take care of those derivatives that we're going to have. So I'm going to extend it a little bit. This is when the function is differentiable. So how about if the function is twice differentiable? You have f double prime. Okay, let's extend it, because your equation may be a equation of a second degree, the third, the fourth, the fifth. Okay, so let's see. I rewrite it here and then I extend it nicely. So what we proved is Laplace of f prime of t is equal to what? Look at the way we write it down. S Laplace of f of t. Then it's going to be minus f of 0. Now if you replace f by f prime. Okay, we assume that the function is twice differentiable. Okay, if you replace f by f prime, what are we going to get now? Over here, we get the Laplace of f double prime. F is f prime, prime would be f double prime. And here you get s times the Laplace of f prime of t minus f prime of 0. Okay, and you know the formula for the Laplace of f prime. This is the Laplace of f prime. So substitute for Laplace of f prime. What are we going to get now? It's going to be equal to the s times, let's have a bracket here, Laplace of f prime. Laplace of f prime would be s Laplace of f of t minus f of 0. You see, minus f prime of 0. So if you distribute it, that give you a form that you can guess what's going to be on the format in general. So that give you s squared. S squared, the Laplace of f of t minus s times f of 0 minus f prime of 0. See, that would be the formula for the Laplace of f double prime. So if the differential equation is given to you, you can change the Laplace of f prime and f double prime into the, look at this format. So we can guess what's going to be the next one. We see we start with the power of the s that's going to be equal to the order of differentiation. S squared. S squared times the Laplace of f of t. Then you reduce the power of the s. You see that's s squared. S to the 0. S to the 0 is 1. Then as you move on, you start with the f of 0 first. F of 0, f prime of 0, f double prime of 0, etc. If you start with the f double prime, you end up with the f prime here. Okay? Can you do the third derivative now? See, similarly, it's a bit. It's going to be Laplace of the third derivative. You see, you start with the power of s. This is 3, so it's going to be s3, s cubed. S cubed Laplace of f of t. Then you reduce the power of s, which is going to be s squared. It's going to be s squared times f of 0, the function. Then you reduce it again, minus s, but you multiply f prime of 0. Then you reduce it again. When you reduce it, you get 0. S to the 0, which is 1. That times it by f double prime. You see, you start with the third derivative, but you end up with the second. So this is the way you're going to do this. One more, you're going to need this one because it is one of the problems that we have. How about the fourth one? You want to do the fourth one? You start with the s to the 4. S to the 4, the Laplace of f of t. You reduce the power of s cubed, f of 0. S squared, f prime of 0. S, f double prime of 0. Minus the third derivative of f times 0. Yes.
So the beginning is always the same, like it'll match the derivative, but the degree of the exponent for the s goes down, but then
It's going down,
but then
and you increase the order of the derivative of the f of 0. You see, this is, this is the 0 order. First, the second, the third, and you differentiate. Okay, or you can have it in general. See, if you want to have, this is it. If you have the n derivative, for example, you divide the s to the n f of t. That's your first step. Then you reduce it, s to the n minus 1. Or you bring the order of the derivative of f of 0. This is the 0 order. Okay, and then you continue, s to the n minus 2, f prime of 0. You just moving on. You see, the last one would be f of, start with the n, you end up with the n minus 1. Minus 1 and 0. This is going to be the most general formula. It's the only thing that we need. The differential equation is given to you quickly. You take the Laplace transform of both sides. Then you change all the derivatives by this formula. When you apply this formula, all the derivative will be changed to the Laplace of f of t. So you have an algebraic equation to solve. Solve the equation in terms of L of f of t. Okay, I'm going to explain the procedure for solving that differential equation. And then that's all we need. We need Laplace inverse. Because when you solve that equation, then you have to find the Laplace inverse. Okay, so let's give you a remark of how we're going to apply it. Differential equation, that's it. So this is it. As we talk about it, the Laplace transform. Okay, Laplace transform can be applied. So to solve a special equation, of course, to solve, okay, to solve a linear equation, with constant coefficient. It doesn't matter, homogeneous or non-homogeneous. With the constant coefficients. Constant coefficient, of course, and the given, with the given initial condition. With the given, we need initial condition as a given initial conditions. Okay, with the initial conditions, initial means at t equal to the 0. Okay, if you like, at t equal to the 0. Okay, in order to do it, this is it. I changed the notation, okay, it's up to you, but I go with f of t. In your book, they go with the y, lowercase y, uppercase y. That would be confusing. F of t and, f of s would be better. So in this method, this is the way we do it. In this method, we assume that the solution is this. Assume that y equal to the f of t is the solution of the equation. The solution of the differential equation. Okay. This is your first step. Then you take the Laplace transform on both sides of the equation. Take Laplace transform. Transform. Okay, on both sides. Sides of the equation. And use the following formula, okay? Use the Laplace transform, use the Laplace transform derivatives. The derivative is function. Okay, functions. This is it. The formula that we talk about, I repeat it again. The Laplace of n derivative of the t, f of t, s to the n, Laplace of f of t, and you reduce the power, minus s to the n minus 1, f of 0, and we just continue, depends on the order. It's going to be minus f to the 0. Okay, you're going to use this one to write the equation. Okay, you apply this one, you simplify it, and you solve the equation for Laplace of f of t. Are you done? Going to the next page. Okay, you use this Laplace of the derivatives functions and simplify the result and simplify. Okay, we're going to simplify the equation. Simplify the equation to convert it. Okay, to convert it into the following form. Okay, into the following form would be, on one side you have Laplace of f of t. Okay, on the other side you are going to have a function or functions of s. You take the Laplace transform, Laplace inverse. If you get this one, then f of t equal to the Laplace inverse of g of s is the solution of the equations. That's it. So the main part really is that last part. And those Laplace inverse would be one of those that we discuss. Okay, sometimes it's going to be more, it depends on the situation they're going to have, okay? But for the time being, all the formulas are standard, you don't have any extra job to do. But when you're done with your quiz, we go back to the piecewise defined function, those are going to be a little bit more involved, they teach that. But for the time being, no. Okay, we give it 2 on this quiz to solve the class, okay? So let's get practice, and then we have some on your practice quiz, we can check that one too. That's it. What we have to do for as we go on, because the function getting more complicated, the equations, so we may need more tools for that Laplace inverse, that last one. This is going to be our job. So for the time being, your result is e to the t sine t cosine t, but later on you may have t squared e to the t times sine t cosine t. So we have to prepare you for those. But the action are going to be all the same. It's not going to be anything complicated. There you are. We want to solve the differential equation. Solve each differential equation. Okay, solve each differential equation. Of course, using Laplace transform. Using Laplace transform. Remember, you have to use this method and not anything else. So let's try the first one. They are going to be very standard. Y double prime minus y prime minus 2y equal to the 0. Y of 0 is equal to 1. Y prime of 0 is equal to 0. We give a 2 question on this quiz. One is homogeneous equation. The other one is, of course, non-homogeneous. Instead of the 0, you may have something else. And that function is not going to be complicated for the time being, because you can't do all of this. There you are. You ready? Solution. I changed the notation. If you don't like it, you don't like to change the notation, it's up to you. In your book, they talk about it. They stay with this lowercase y right through the end, but f of t would be better. You see, it's more familiar. But if you don't like it, you want to use different notation, I don't like that. I'm not going to use it. So there you are. You are going to suppose y equal to the f of t is the solution of the equation. Is the solution. Solution equation. Okay, so that's it. So take the Laplace of both sides of the equation using this equation. Okay, so this is it. I find the Laplace of, okay, the Laplace of what? F double prime of t minus f prime of t minus 2 f of t. This is the first part, equal to the Laplace of 0. So I take the Laplace transform on both sides of the equation. Simplify it. The Laplace in linear. So break this one, expand it. So that gives a Laplace of f double prime of t minus Laplace of f prime of t minus 2 Laplace of f of t. Laplace of 0 is 0. If it's not 0, it's going to be anything else, you substitute. If it's happened to be sine, you substitute here right away. Sine of t, you know that. It's going to be 1 over s squared plus 1. So that's the first step. Next, change this f prime, f double prime, bring the formulas. And we talk about it. Okay, so there you are. Write the formula for f double prime. F double prime, remember you start with the s squared, Laplace of f of t, reduce the power of s minus s times f of 0 minus f prime of 0. This is, I just replace that Laplace of f double prime. Okay, any question? Minus, repeat it for the next one. Next one, you can do it right away or just bring it and apply the negative sign, depends on how you're going to do it, f prime. So the power is what? S Laplace of f of t. Reduce the power, it's going to be just s to 0, which is 1, so that give f of c. This is where you substitute for the L of f prime. You repeat the rest, it's minus 2 Laplace of f of t equal to the 0. Now we have to do the algebra. Apply this negative sign, okay? So I have s squared Laplace of f of t minus s f of 0 minus f prime of 0 minus s Laplace of f of t plus f of 0 minus 2 Laplace of f of t equal to the 0. Okay, that's going to be the case. Now apply the initial condition. Initial condition that you have is what? So your initial conditions are going to be, this is it. You have f of 0 equal to the 0. F of 0 is equal to 1. F prime of 0 is equal to the 0. So this f prime of 0 would be 0. We are going to rewrite this one. Okay, so this is going to be the result. You see f prime of 0, 0. This is 0. This is 0. F of 0 is 1. Then f of 0 is 1. We'll repeat it again. Simplify it. So we are going to have s squared. S squared Laplace of f of t. F of 0 is 1, so that gives minus s. F prime of 0 is 0, disappear. Minus s Laplace of f of t. Okay, f of 0 is 1, plus 1. Minus 2 Laplace of f of t equal to this. Any question? So you apply the initial condition here. Now you get an equation, the unknown of Laplace of f of t. Okay, you cannot combine these like terms, okay, but you factor it out, you see, you have 1, 2, 3. Factor out the Laplace of f of t, the leftover would be, get s squared, okay, minus s, minus 2, Laplace of f of t. Anything else, you move it to the other side. So we have a negative s here, we move it to the other side, make it to the s, minus 1. Any question? You stop and you check. You see this coefficient? This coefficient must be always like the characteristic equation. Remember, the equation is linear. It must be the same as the characteristic equation of the given equation, homogeneous equation. Look at the equation that you have. You see characteristic equation, remember? R squared minus R minus 2. So this coefficient always must be the same thing. S squared minus S minus 2. So if you get something else, probably you missed a sign or something, okay? So check this one. You see, as soon as you get, you check this one. Okay, this must be characteristic equation of the homogeneous equation. Now we solve for the L of f of t. You divide both sides by s squared minus s minus 2. So the other side was 0, so this is every 1. So this is going to be 1. The Laplace of f of t is going to be, we have s minus 1 on the other side. Okay, and this is s squared. Okay, s squared minus s minus 2. That's it. So that's a g of s that I talked about. So now you know that f of t would be what? F of t would be Laplace inverse. Okay, Laplace inverse of what? Laplace inverse of s minus 1 over s squared minus s minus 2. So your job is to find the Laplace inverse. So your all of them would, end up with this. So in order to find the Laplace inverse, you check denominator. In this case, it's factorable. For the time being, are going to be all factorable. Later on, it can be the one that is not going to be factorable. We take care of it. Okay, so break this one again, partial fractions. So it's a s minus 1 divided by what? Partial fractions would be factor it, s minus 2 times s plus 1. Okay, denominator. So break it into part, s minus 2, the a1 on the top, and s plus 1. Okay, s plus 1, you put the a2 on the top. Continue as usual. It's going to be equal to the top. It's a1 times s plus 1 plus a2 times s minus 2. Denominator as is. Again, carefully let the top two become to each other and take it up. So it's going to be a1 times s, okay, times s plus 1 plus a2 times s minus 2. And this is equal to the s minus 1. The top to be equal to each other, both sides. No check numbers. Zeros of the denominator, 2 and negative 1. So if you put s equal to the 2, so that give you a1 times 2 plus 1. Okay, this would be 0. And this is going to be 2 minus 1. So that give you 3a1 equal to 1. So a1 would be 1/3. That's the first part. Okay, any question? So continue, the other zero is a negative 1. S equal to the negative 1. You substitute, this one would be 0. So that gives you 0 plus a2. And that's a 1, negative 1. Okay, negative 1. Negative 1 minus 2. It's going to be negative 1 minus 1. Okay, negative 1 minus 2 would be negative 3. So that gives you negative 3a2 equal to the negative 2. So a2 would be 2/3. Okay, now we are ready to review the result. So there you are, Laplace inverse of missing one, s minus 1, s squared minus s minus 2 would be equal to, can break it as is, see a1 over, a1 is 1/3, so it's going to be Laplace inverse of 1/3 over s minus 2. Okay, that's it. Then 2/3 for the second one, plus the Laplace inverse of 2/3. Okay, 2/3 over s plus 1. Plot the numbers and the rest are just exponential functions. Okay, so this is going to be 1/3. Laplace of 1 over s minus 2 will be e to the 2t. Okay, this is going to be 2/3 e to the negative. That's your function solution. F of t is equal to 1/3 e to the 2t, okay, plus 2/3 e to the negative. See, it's a nice method. It's initial value for quickly you get, you get the result right away. Okay, any question? So it depends what you are going to get right at the end. The different problem would have different, yes.
Can you go to like with the problem?
Beginning,
Yeah. Because I was like catching up, but I got negative f prime of 0. So then I had a negative 1.
f prime of 0, f prime of 0 is 0.
Oh, f prime of 0 is 0.
Yeah, it's given to you.
And then what's f of 0? Oh, okay, I see. Okay.
Okay, any question? So you may have higher order. Okay, this one is from the, I think it's a practice. It's the same as the practice. It's a very popular problem. So I do it as well. We see what's going to be the higher power. Don't be afraid of the power. You may simplify that at the end to give you something nice. Okay, so this is going to be our second one. Yes,
Isn't it one minus S? Why is it S minus one? The,
the formula is Laplace of e to the at is 1 over s minus a.
no, I know, but like for the beginning, I was getting one minus S times f of 0.
Where is that?
Like if you keep going.
There's a negative s here, okay, negative s, this will be 0, negative s plus 1. Right, that will be s minus 1.
Oh, okay, I see.
The 1 minus s is when it's on the left.
Right. Yeah.
Okay, any question? Yeah, break. Okay. Yeah, we give break. So I do this one when we do the break. It's the same one.
Sorry.
I don't think so.
Right around, right before it says end.